Yeah, so we continue talking about the representation theory for generally algebra G, and we have considered two nilpotent elements. Of course, there are way more nilpotents, so I want to kind of talk a little bit of how they look like. So it's 1, 4, 3, I guess, and it's about general chi. So let's talk about nilpotent orbits. And from what was said before, it's enough to consider orbits just in the algebra G. So how are they classified? So if G is SLN, as you know, nilpotent orbits are classified by partitions of n. And this is via Jordan type, right? And for other classical Lie algebras, the story is similar, only you need to only consider certain partitions. Namely, nilpotent, so here it's convenient to look at disconnected group ON. Nilpotent ON orbits in SON are in one-to-one correspondence with partitions of N where each odd part occurs with even multiplicity. Sorry, every even part. So every even part occurs with even multiplicity. And how do you get this answer? Well, you ask yourself, when does the representation of SL2 has an invariant orthogonal form? Okay? And the answer is here. Now for SP2N, the answer is similar. Let me write SPN. But N will necessarily be even. So you get the same answer, but instead of even parts in the second line, we need to consider odd parts. So every odd part should occur with even multiplicity. Okay? Now, how can we study irreducible representations of a Lie algebra?
Can you recall, you wrote the orbit ON orbits, not SON?
When you look at SON, sometimes ON orbits split into two SON orbits. But they're very similar, so it's we don't really need to distinguish between them. So it's the same partitions of N.
N is even.
Yeah. Okay. So now we want to study the category of U chi F modules. And as before, we want to start by looking at some graded analog. Namely, we pick a maximal torus T0. So it's maximal torus in the centralizer of chi in the group GF. So that's our stabilizer. Then this torus, of course, acts on the central reduction. Maybe I should write T0F. So T0F acts on the central reduction. And just as before, we can look at the category of equivariant modules. Okay? So that's modules graded by the character lattice of this torus, and the action of its Lie algebra is recovered from the gradient. So the same story as before. And now each weight space is a module over Levy. So the Levy, which is the centralizer of T0 in GF. And then again, in this setting, we can play highest weight theory. Highest weight theory is going to depend on the choice of a generic one-parameter subgroup. So let's pick new, which is going to be generic one-parameter subgroup. When you have this, you can get an integral grading on your Lie algebra. So let me denote it like this. So GF splits as a direct sum over integers I, GIF. And we can consider parabolic. GF bigger or equals than 0. And this gives us parabolic induction functor. So baby parabolic induction functor from the category of T0 equivariant module over U0 of GF0 to the category of sorry, it shouldn't be 0, it should be chi like such. So when we write this, we kind of recall that chi can be thought as an element of G0F 1 star. Okay? So it's centralized by the torus. And then, as before, this functor gives an identification of irreducibles in the source category, U chi G0F mod, and irreducibles in the category that we want. Okay? So that's the same story as we did for chi equal to 0, but it's a relative story because our important element is no longer fixed by the maximal torus. It's just fixed by some torus, and so we have a relative version of the constructions that we've done before. And in some cases, namely when chi is principal for G0F, sometimes happens, this gives you a complete classification of irreducibles here. While in general, it only gives you a reduction of classification of irreducibles in this category to classification of irreducibles in this category. Okay? So it doesn't give a complete classification.
In type A.
So in type A, every nilpotent element is principal for some Levy. In general, this is not so. So instead, what we can say so chi is so-called distinguished for G0. So what does this mean? It means that so how should I put it? Let me put it this way. So the centralizer of chi in G modular the center of G is a unipotent subgroup.
And G is the same as GF. G is the same as GF.
Yeah, I need to put subscript F here. So if I take the connected component of the centralizer of chi and G and mod out by the center of G, maybe I should also put connected component here, I get a unipotent subgroup. Or in other words, every torus that centralizes my element is central. So this reduction doesn't produce anything. Okay? So it doesn't reduce to any proper Levy subalgebra. Another way to put it is that an nilpotent element is not contained in a proper Levy subalgebra. So this is, so to say, cuspidal case. We cannot use this kind of induction to study it. How do distinguished elements look like in classical Lie algebras? So when G is equal to SLN, then distinguished is the same as principal. If your nilpotent element has more than one Jordan block, it is centralized by a non-central torus. However, when you are in classical types, like SON or SPN, there are much more distinguished elements. So here, distinguished is equivalent to having all parts distinct. Okay? So unipotent elements are parameterized by partitions, and such a unipotent element doesn't lie in a proper Levy if and only if all parts in the partition are pairwise distinct. So there are quite a few of those.
Just to answer, so distinguished elements are interesting for us because for them we cannot simplify our...
Yeah, we cannot simplify classification for reducibles. So that's exactly right.
Otherwise we have some Levy and then reduce.
Otherwise we have some Levy, and at least on the level of classification we can reduce to that Levy. This reduction doesn't work on the level of characters. For characters it's way more complicated. But if you're only concerned with classification, then we can just reduce to the Levy, unless your element is distinguished. Okay. So now this is kind of a picture that we have. Let me say a couple of words about the picture that we want. So we are studying representation theory and we want to compute well, maybe characters of irreducibles, so classes of K0s in K0, or maybe just dimensions, something like that. So what is the general pattern of doing that? So a general pattern is this. You want to have your irreducibles labeled by something like elements of a Weil group, or maybe a fine Weil group, or maybe some cosets by a parabolic subgroup, or maybe something like that. And you want multiplicities of irreducibles in some standard objects expressed in terms of Kazhdan-Lusztig polynomials. Okay? So that's what we usually want. This is a classical story that we have for BGG category O, where we can split our category into blocks. We can reduce all questions to principal block. In the principal block, simples are labeled by Weyl group elements, and multiplicities of simples in varmas are given by Kazhdan-Lusztig polynomials. Okay? You can also look at parabolic categories O, and there multiplicities are going to be given by parabolic Kazhdan-Lusztig polynomials, and simples are going to be labeled by some cosets. So we want to have such a picture here, and it turns out that indeed we can, which wasn't known until very recently. Before I'm going to talk about what happens for this representation theory, I want to give you a reminder on some Kazhdan-Lusztig theory. Okay? So that's what's supposed to be the second part of this course. So part 2, it's classes of simples in K0. And Kazhdan-Lusztig theory. And let's start with a reminder on Kazhdan-Lusztig. So what Kazhdan and Lusztig did, among other things, they defined a distinguished basis in a Hecke algebra. So let me start by reminding you what a Hecke algebra is. So let's take a Coxeter group, W with a set of simple reflections I. So it's going to be Coxeter group. And let's take V to be indeterminate. So from here we can produce an algebra over Laurent polynomials in V called the Hecke algebra. And I will denote it by H sub V of W. So what is this? You take the group algebra of the braid group. So this fellow here, B sub W, is a braid group. You adjoint V plus minus 1, and you mod out by relations Ti minus V, Ti plus V2 minus 1 equals 0, where I is in I. These are generators of the braid group corresponding to simple reflections, and you impose this condition. So if V is equal to 1, then what we get is just Ti squared equal to 1, and you recover the group ring of W. In general, you get a flat deformation. So this algebra has basis TW, called standard basis, where W is an element of the Weyl group. And what Kazhdan and Lusztig discovered like 30 years ago is that one can define another distinguished basis called Kazhdan-Lusztig basis. For this, we need a certain ring automorphism called bar involution. which I'm going to denote by A going to A bar. So what does it do? It sends V to V minus 1, V to power minus 1, and it sends Ti to Ti to power minus 1. And on the basis it sends TW to T of W minus 1 inverse. Okay? That's an ring automorphism. And then there is a following result of Kazhdan-Lusztig. That there is a unique basis again indexed by elements of W. Let me call it C sub W of the Hecke algebra, such that, so first of all, each CW is invariant under the bar involution. And second of all, so each CW lies in TW plus V times the span over ZV of other basis elements, TU, U, and W. Okay? So when you decompose your new basis in terms of the standard basis, all the coefficients are polynomials without constant term, with exception of coefficients of TW, which is 1 plus such a polynomial. Okay? And then once you show this uniqueness, you can also show that the coefficients are only going to be non-zero if U is less or equal than W in Briard order. Okay? Which allows to compute this basis recursively. This can be algorithmically computed, although formulas are not easy in any sense. Except in some special cases. So let me give you some examples of how the CWs look like. So example, well, the most pleasant one is C of 1, which is just T of 1, and that's a unit in your algebra. What is C sub Si? It's Ti minus V. That's a very simple formula. And let's put it this way. If W is finite, then we can talk about the longest element, W sub 0 in W. Then we can somewhat surprisingly write a very explicit formula for CW0. This formula is quite simple. So it's the sum over all U in W of what? Of negative V to power LW0 minus LU times T sub U. Okay? And moreover, this can be slightly generalized. Namely, if you take some finite parabolic subgroup of W, then the formula is going to be the same where you sum over elements in the parabolic subgroup. So these elements are easily computable, but in general there is no explicit formula. Questions? So now I want to talk about some related notion, the notion of a cell. Below we'll need to talk about cells. And this is a pretty general notion. If you have an algebra with a basis, then you can get a preorder, a partial preorder on the elements of the basis by inclusion of left ideals that they generate. So let me write it down. So we define, so for U and W in W, we say that U is less or equal than W. So by definition, this means that the left ideal generated by C of U is contained in the left ideal generated by C of W. Okay? And then we have a notion of equivalence. U equivalent to W by definition means that U is less or equal than W and W is less or equal than U. And by a left cell, we mean an equivalence clause. So left cells are equivalence classes. For this equivalence relation, so some remark. We can also consider right or two-sided ideals, and we will get notions of right and two-sided cells. And in classical types, you can describe cells combinatorially. I'm not going to do that. Peculiarly, there is no combinatorial description of this preorder, even in type A. So nobody knows what it looks like. Okay, so let me just give you an example. So example. So let's say that J inside of I is of finite type. Then I'm going to define a subset W superscript J. This consists of all U in W such that U is longest in its left W sub J coset. So W sub J is a corresponding parabolic. Okay? And then, of course, I have the longest element, W0 sub J. That's the longest element in W sub J. And then one can show that W superscript J is in fact all elements in W such that U is less or equal than W0J. Okay? This has to do with this simple description of the corresponding Kazhdan-Lusztig basis element. All right. So this was a brief reminder of Kazhdan-Lusztig theory. Questions?
How many cells are for SL3?
Left cells 4.
And what is a parabolic subgroup?
Parabolic subgroup is a subgroup of all elements generated by generators lying in some subspace, in some subset of I. It corresponds to a Levy, or if you want, to a parabolic subgroup in G.
Can you say to us what does example mean? What is example of what?
It's example of the pre-order. So I want to describe all elements which are less or equal than this one.
This element is longest in the parabolic group.
Yeah.
And what is the answer?
The answer, all elements lying in this W superscript J. That's a very explicit subset, right?
Yes.
Okay.
And why do you define W with upper script J?
Well, because it's a standard notation. W lower J is parabolic subgroup, and this W superscript J is this complementary set of longest coset element representatives. So it's a subset in W.
I see.
Also known as a set of labels for parabolic category O, by the way. Okay. So now let me tell you kind of what was the state of the art before our work. So below I talk about joint work with Bezrukovnikov. And before I get to that, let me tell you what was known. Okay? So known before that. So first of all, people knew the K0 group of modules over the central reduction U chi 0. You actually can put a different Harish-Chandra character here. If it's regular, then the answer will be the same as here. If it's singular, you will need to take the corresponding subset. So let me concentrate on the 0 Harish-Chandra character. So, and this was identified by Bezrukovnikov, Mirkovich, and Romanian with K0 of coherent shifts on the Springer fiber. Of chi. Okay? So Springer fiber of chi consists of all barrels containing this nilpotent element. So it's some singular algebraic variety. You can look at coherent shifts and take K0. You get some finitely generated free Z module. And this finitely generated free Z module is this K0. And I will explain why in the next part, meaning on Tuesday. And then Lusztig conjectured that there is a canonical basis in this K0 which on the representation theoretic side gives the basis of simples. So given basis of simples. So let me say just a couple of words. It's not going to be relevant for what follows. So there are various settings where you can talk about canonical basis. And in all these settings, you need to have a module over Lorentz power series. In this module, you need to have a lattice, and you need to have a bar involution. And basically, I mean, what Lusztig does, he sort of gives you this data. I mean, there is also relevant data of sesquilinear form. In any case, so there is some description of a basis in a graded lift of this guy. And the only thing that you need to know about this basis is that it's very difficult to deal with. First of all, it's not obvious that it exists. Second of all, even if you know that it exists, it's very difficult to compute. Okay? So this result, so this was proved by Bezrukavnikov and Mirkovich. And not only you cannot read the dimension formulas for the simples out of this result, you cannot read combinatorial classification. Okay? So there is no explicit combinatorial set which will label elements of Lustig's canonical basis. So this is sort of unsatisfactory. And the goal of our work with Roma is to give explicit combinatorial classification and to give character formulas by which one should mean formulas for K0 classes of simples in terms of Kazhdan-Lusztig basis. Okay?
So with combinatorial classification, I mean just you want to produce a finite set.
I want to give you a description of a finite set which labels certain irreducibles.
So in particular, you're going to produce some explicit finite set whose cardinality will be equal to the
No.
ring of fiber.
No. That's not what I'm going to do. So the whole secret is that this is not quite the category that you should consider. We'll consider a closely related category for which all these problems, combinatorial classification of simples and character formulas, become as explicit as you could hope they would be. Okay? So the whole secret of this story, which apparently wasn't realized by Lusztig, is that this is not a right object to consider. So you need to slightly modify it, and that's what I'm going to do next. And for time being, I will concentrate on the distinguished case. So it's, I guess, 2 times 2. And it's going to be about certain equivariant modules in the distinguished case. Distinguished case means that my nilpotent element chi is distinguished. Meaning it doesn't lie in any proper Levi subalgebra. And so what about equivariant modules? Well, I can consider the stabilizer G of chi, and this, well, let's assume that G is semi-simple for simplicity. So the connected component of this fellow is unipotent. And because of this, it's a semi-direct product of some finite group, which I will call A, with the connected component. So this connected component is a unipotent subgroup. And what I want to look at, I want to look at the category of equivariant modules. So I take the trivial Harish-Chandra character, and I look at equivariant modules with respect to action of this finite group. In the usual sense, I mean, it's kind of, there is no continuous part here, so there is no condition of the differential or anything. Just modules equivariant with respect to this finite group, which of course acts on our algebra. And so this happens to be the right object to consider. This is the object where all the answers are as nice as you could hope they be. And first I'm going
to look at the whole group of connected components, not some kind of Lusztig quotient or something.
No. Just the whole component group. And the first thing that I want to talk about will be standard objects in this category. So let's look at the whole p-central reduction UKF. So in order to do this, I will need to recall a few facts, a few additional facts about distinguished nilpotent elements. Namely, let me write this fact as follows. So distinguished implies something that I will call birationally Richardson.
About notations. You sometimes write U0 F high, sometimes
so, right, but this is a subcategory of all objects in here where the Harish-Chandra center acts via this central character. Okay?
Yes. So you're going to, at the end of the day, you're going to describe this?
I am going to describe standard objects in here, and there will be standard objects with this central character. They will lie in here. Okay? So let me explain what birationally Richardson means. So birationally Richardson means the following. So there is a parabolic subgroup PF inside of GF such that, so first of all, chi, so when you have a parabolic subgroup, let me introduce the standard notation. The parabolic subgroup is going to be a semi-direct product of its Levy and its unipotent radical. Okay? So the condition that I want is first that chi is conjugate to a generic element in NF1. Okay? So it's conjugate to a generic element in the nilpotent radical. Equivalently, this can be stated as follows. So the orbit of this chi is the image of the cotangent bundle T star GF1 mod PF1 in GF1 du. So this variety maps to this variety in a standard way. It's usually called Springer map. And the condition that I have here is equivalent to the claim that the orbit closure of chi is the image of this map. This is what is known as Richardson element. Now, birationally Richardson means
maybe that's an annotation. So suppose your element is the principal nilpotent.
yeah.
Then what is the statement there?
Then I take P equal to B, and the statement is that the image of the Springer map is an important cone.
Right, but you wrote n of 1. And this
Yeah, I mean it's just kind of tracking which space it lives.
no, I mean maybe that's not what one. So what is?
It's Frobenius twist.
Frobenius. Okay, sorry.
So birational Richardson is a property of chi, right?
Yeah, of the orbit of chi. So that's a Richardson property. Now what birational refers to is that this map from GF1 mod PF1 to the orbit closure is birational. In general, it's kind of several to one, but sometimes it's birational. For example, every nilpotent element in SLN is birationally Richardson. That's a standard fact. But also every distinguished element is birationally Richardson. So now with this, what can I assume? So we can assume two things. We can assume, first of all, that chi lives in NF1, and equivalently, if you want to view it as a function, then chi paired with PF1 is equal to 0. And therefore, the 0 central reduction of PF embeds into U chi F. Okay? It's just subalgebra here, which is generated by the elements in this parabolic subalgebra. And then I can also assume that A, this finite group that I introduced before, lies inside of LF, inside of a levy. It's kind of the same story as you would have in characteristic 0. There is no, there is no characteristic P effect on this statement. Okay? The same statements are true in characteristic 0, and you have the same conclusions. So now what I want to do, I want to produce standard objects in this category. And standard means that these are objects that I can control in some sense. So, and these standard objects are going to be parameterized.
So standard objects in this category will produce a basis on the Waterman group of this category.
They will produce a generating set.
So the number of standard, you wanted
the number of standards will be bigger than the number of simples. In particular, this number of standards will be infinite. Okay? So let me take mu, which is a dominant weight for the levy L. And from this I can produce the so-called dual while module let me write it WLF of mu. So what this means is that it's just global sections on LF modular LF intersection with BF. So that's a usual Flach variety for L, or of the corresponding line bundle, O mu. Okay? In characteristic 0, this construction gives you an irreducible. In characteristic P, this construction gives you an object which will be reducible, but which will have the same character as in characteristic 0. The character is still given by Weil character formula. Okay? So this gadget is LF module. With character given by Weil formula. So that's a module over group. In particular, it's a module over this Lie algebra. Okay? With 0 P character. And then I can inflate it to a parabolic. So U0 of PF acts on my Weil module. And so does A, because A sits inside of LF. So it's an equivariant module. And then what I do, I will define W chi F of mu to be just a parabolic induction of this Weil module. And this lives in the equivariant category that I want. Okay? Not only it lives there, it's very easy to control the dimension. So the dimension of this parabolic induction as usual is equal to P to the dimension of n, or maybe I should write dimension G mod P, and then multiply by the dimension of the Weil module. Okay? So that's something which is computed in elementary combinatorial terms. So the secret to this formula is that so this P-central reduction is going to be a free module over this algebra, and the rank is going to be precisely P to dimension of G mod P. Okay? It's again this Poincaré-Bergov-Witt statement. Okay?
And why does P-center text by 0?
So, okay, so there is a Levy part and there is a unipotent radical part. For the unipotent radical part, I just inflate. It acts trivially, in particular, P-central character is 0. And then if you take a module over a reductive algebraic group in characteristic P, and you restrict it to Lie algebra, then the P center acts by 0. So so unlike in characteristic 0, there is no direct correspondence between modules over Lie algebras and algebraic group in characteristic P, in particular because only simples with 0 P character come from algebraic group. Okay? And you can see it as follows. So let's take a module over an algebraic group. Let's restrict it to a Lie algebra. What is a P character? Well, I mean, whatever it is, it's invariant on the action of the group. Because the action of the group, when you conjugate your Lie algebra module by a group element, it's still isomorphic, right? So in particular, the P character is stable. And if your group is semi-simple, the only option is that this P character is 0. Of course, here it's reductive, so you need to say a bit more words, but I mean. Okay. So these are standard objects in this category here. They are labeled by dominant weights. The last thing that I want to discuss today, and then we'll continue next time. So let's say that today I don't go over time, but tomorrow it may become somewhat different. Okay? Okay. So what about Hristianda characters? Well, what is Hristianda character of this object W chi F mu? Well, again, it's a parabolically induced module, so the Hristianda character is computed in the usual way. So it's the W orbit of mu mod P. In particular, I can describe all standards which lie in the category with 0 Hristianda character. So the standards in U chi 0 F mod the following fellows. It's W chi F of W dot minus 2 rho. Okay, those are precisely weights which correspond to modules in the 0 Hristianda block. But we also want this weight to be dominant for L, right? So what is this condition? This condition is precisely
Here, little double is in there. I'll find it.
Yeah. It's precisely the W lies in longest coset representatives for P. Okay? So the W lower P is just a parabolic of P. In other words, we have standards labeled by the
W with a P.
So these are longest coset representatives.
Oh, it's like we had.
Yeah, it's like we had in the discussion of Kazhdan-Lusztig theory. So the standards in this object, in this category, are labeled by the same set as parabolic Verma modules in a principal block of affine category O. And then we will see a couple of things. So I will state this result tomorrow. Let me just give you a brief overview of what this result looks like. So what you see here is that I have infinitely many standards. And what I consider is a category of modules of a finite dimensional algebra which are equivalent with respect to finite group. There are only finitely many simples in that category. Okay? So this cannot be a basis. Instead, this can be shown to be a generating set. Okay? So the classes of these objects generate K0 of our category. And you can ask how to express classes of simples. And classes of simples will be expressed via parabolic affine Kazhdan-Lusztig polynomials. And the simples are going to be labeled by while group elements which lie in the left cell of W0.
So this is the advantage somehow of considering this A covariant.
Yes.
So,
Yes.
I mean, this is the most trivial place.
Yeah. Yeah. So the usual modules are not labeled by anything which is any good. Equivariant modules are labeled by elements of the left cell. And in this kind of world, it's as explicit description as you may want to have. And of course, if you want to prove such a statement, you don't prove it numerically, you prove it categorically. So let me write you a categorical statement which is not going to make sense as written, but we can make sense of it.
Sorry, and this is going to be which left cell? Or?
It's a left cell, which is the maximal left cell in this press cell. So this is kind of, these are all elements which are less or equal than W0P. Okay? And we will take the left cell of W0P. We'll take the top left cell. So let me modify notation here a little bit, zeroing round brackets.
Sorry, if I can define it,
Yes. Well, I mean, no, Sasha, it follows from the claim that the element is distinguished. If you take just any parabolic, then the cell is going, for an arbitrary parabolic, the cell may be infinite. It follows from the coherent description of...
is it possible to see it explicitly in terms of P? I mean, if you take some P, how to see that corresponds to the distinguished element? This is difficult, right?
I have no idea. Okay, so I consider this category, and what zero in round bracket means is a generalized Hristian character. And so the result about this category is that, so this fellow is a quotient category. Maybe I should write cell quotient category of affine parabolic category O. Which cannot make sense as stated, because affine parabolic category O is over complex numbers, and this category here is over field F. So instead, you need to work with a characteristic zero incarnation of this category. And next time I will talk a little bit about what it is, and then the statement becomes true. And with such a categorical statement, it's the statement on the level of characters, which I will state tomorrow.
Is it the affine parabolic category O on what level?
Negative, principal block.
Principal block.
Okay, so let me tell you a little bit of what's going to happen tomorrow. So tomorrow I'm going to repeat some of this stuff. I'm going to write the character formulas. And I'm going to start explaining how such character formulas can be proved. Basically, for this, you need to know derived localization characteristic P, which I will talk about. And you will need to know this equivalence between two different versions of affine Hecke category, which I will also explain. And then maybe in the after part, I will explain how some actual proofs go. Okay, for today, that's it.
So we resume a good journey.